Welcome my friends, welcome to my next lecture. So in my last lecture, if you remember, I talked about the existence of or how to find local or global extremum, okay, for given a functions and given a scalar field. In particular, if I have a function from say R2 to R, then is there a way to talk about the existence or critical value, or there is some points where I can say that okay, yes, my functions attains extremum, that is maximum and minimum locally. And there are certain things I have discussed like quadratic forms, then corresponding symmetric matrix, and then there is a relations with the Hessian, and then how the Hessians or characterization of Hessian matrices give you some conditions on your functions that these are the points you may look for, your function might attain some extremum. So those are the things I have discussed. Now this lecture I will talk about again the bit of extremum as well, but this time I will talk about global extremum, that means global maxima and minima. That means if I have a set which is not open, so that means if it has a boundary, then as I said earlier, that means to talk about or to find about the extremum points, you have to, or critical points, you have to see the interior as well as in the boundary points to talk about whether global extremum exists. So that I will talk about first, and then of course there will be a concept called constrained extremum problem, and that one can handle with the concept of Lagrange multipliers. Along with at the end I will talk about what is called exact differentials. Okay, so as I said, so I should start with the existence of global extremum. So I start with an examples. So I am written this is global extrema, that means it could be global maxima or global minima. So this is the examples I would like to investigate. So I am saying that okay, find global maxima or global minima for the function, these functions. Now look at this function, these are functions of polynomials, right? Very nice functions, it is differentiable. In fact, one first differentiable, first order partial derivative exists, second order partial derivative exists, they are continuous, this is differentiable, it's a very nice function. But I want that function should be defined where? Minus 2 comma 2 cross minus 2 comma 2. So that means I want the existence of global maxima, global minima in this region actually. So this is the region, square region, okay? So this is actually your 0 comma minus 2, okay. So 0 comma minus 2, so this is 2 comma 0, okay. This is 0 comma 2, this is 0 comma minus 2. I think this should be x, okay, sorry, this is minus 2 comma 0, yeah. So this point. So that means I have a function, I have a very nice functions, and I have a say square region. Now square region, it is not an open set because minus 2 and 2 is included. That means it will have a boundary. This is a boundary. So that means if I want to find the points of extremum, that means I have to look the interior along with the boundary, as I said earlier. Okay, so how to do that? Now to find global extrema, so find extrema of f in the interior, as I said, in the interior, and then one has to check with the boundary point as well. So in my last lecture I said, so if you have a set, if I have a functions and if I want to check the point of extremum in that set, and if that set has a boundary, then you have to look at the boundary point along with the interior points, okay. So now to talk about the interior points, so you have to find the critical points. Now all the first order partial derivative exists, so therefore you just solve the partial differential equation, that means make the first order partial derivative fx fy, put fx is equal to 0, fy is equal to 0, and the solution will give you the critical points interior, some point critical points, okay. So that's you can easily do that. The function is very nice, it's a polynomial in x and y. So if I take the first order partial derivative, it is 4y minus 4x, you just equate with 0. Consider del f del y, which is f suffix y, which is 4x minus 4y cube. Now if I solve these two equation, fx is equal to 0 and fy is equal to 0, you will obtain these are the points 0 0 1 1 and minus 1 minus 1. These are the three interior points which are critical points. So there I have to check whether maxima minima exist or not, okay. If just check the value f11, f minus 11 value is 1, okay. Now what about the point 0 0? If you check the point 0 0 is a saddle point, that means what? That means you just compute the Hessian matrix and think about the determinant, you will see determinant is negative. So therefore 0 0 is a saddle point, so that means maxima minima might exist at the point 1 1 or minus 1 minus 1, okay. But I am talking about, or I want to find those points where global maxima, global minima exist. So these are the interior points or critical points where we have something will happen like maxima minima. So 3 points, 0 0 is a saddle point, you just omit that one. So in the interior you will have only 2 points, 1 1 and minus 1 1, and the corresponding value is 1. Now let's see the boundary points. Now if I have the boundary points, so boundary is very nice, it's a line, combination of line, right? So in the boundary what you have to do, so look, you have to consider this function. So that means what I am doing, I am just fixing my second coordinate y is fixed, or first coordinate x is fixed, and then I am thinking about the functions of a single variable, right? So therefore if y is equal to 2, then it is a function of single variable defined on your minus 2 to 2. So you have to just find the extremum of that single variable functions on the closed interval minus 2. So that means what you have to do. So when I am fixing y is equal to 2, that means what I am doing is that I am actually in that line, okay, y is equal to 2. So fix y is equal to 2, keep or think of function as a function of x variable defined in the interval minus 2 to 2, and find the extremum. Similarly, if I keep y is equal to minus 2, that means I am in that line, this line. Similarly, if I x is equal to 2, that means I am in that line, and if I have x is equal to minus 2, that means I am in. So that means in the boundary I am keeping one variable fixed, think about is a function of single variable defined on minus 2 to 2, you get the critical point and you compare it, that's it. So if just for example, if I just think about this function f of x comma 2, so if I write gx, which is exactly equal to your f of x comma 2, and what is this function, f is given, right, what it will give. So this should be y is equal to 2, so that means this should be 8x minus, so this should be 2x square, and then y4 means 2 to the power 4, then it should be 16, okay. So this is my functions defined on the interval minus 2 to 2. You just get the critical points. Again, just take the derivative of g. What is the derivative? Derivative g prime at x, what will happen? This should be yes, 8 minus 4x, this is equal to 0, that means it will give you x is equal to 2, correct? So that means the corresponding critical point is 2 at x is equal to 2. So that means you have to just evaluate what is the value of f22, okay. So that means you just calculate the value f22. If I calculate the value f22, I think it will give you what? So these are the critical points. That means there is a possibility of having maxima or minima at that point. X is equal to 2 and y is equal to I have fixed, so that means the point only 2 you should consider. So if I consider f of 2 then what will be the value? That means this should be 16, okay, minus 8, then minus 16, this should be actually minus 8. This is one of the value, okay. And that's why you should consider, you should deal with this function, and these functions. So think about it as a function of single variable on the interval minus 2 to 2, get the critical point and take the value, because you have only finitely many points will be there, and you just compare at which point my functions attains global maximum, global minimum. If you do that, then I have written that global minimum attained at the point 2 comma minus 2 and minus 2 comma 0.2, and what will be the value? Value will be minus 40. And what about the global maxima? Global maxima, you will have only 2 points, 1 1 and minus 1 1, and global maximum value will be 1. So that's how you have to do. So this is a very simple example, but in this example, what is the difference with the earlier example is that earlier we will have an open set, that means only the interior point, and if your function is nice, you just take the first order partial derivatives, equate 0, get the solutions, these are the critical points, and then talk about the corresponding Hessian matrix at that point, and depending on the behavior of the Hessian matrix, you can say that, okay, whether my functions attain local maxima, local minima, or it is a saddle point. So this time it will be little different because I am having the boundary along with the interior point. So in the interior point, you take the partial derivative because your function is nice, equate with 0, get the solutions, critical points, along with in the boundary point you also take care. That could be happen in the boundary point as well, okay. Okay, another example. So again, this is an example. So find the absolute or global maxima minima of this. Again, this is a very nice function. It's a polynomial functions in x and y. It is differentiable, first order partial derivative, second order partial derivative exists and continuous, but this time I want that it should be in the what region? Earlier you see the rectangular region, that this time it's a triangular region in the first quadrant bounded by this. So that means if I have this one, so x is equal to 0, so that means this is the y axis, this is the x axis, so this is y is equal to 0, this is x is equal to 0, and what will happen? X plus y is equal to 9, so that means we will have this. So this is x plus y is equal to 9. So that means I want the existence of some extremum points in this region. So in this case, what is the boundary point? Boundary point again is a line. So it is x axis, y axis, and this one. So again you have to just do the same thing. Okay, so first you think about, or first you get the critical point in the interior, and then you do talk about in the boundary points. Okay, let's see. So to talk about in the interior critical points, you just take the first order partial derivative fx, and you know how to calculate first order partial derivative, keeping y variable fixed, think about as a function of single variable, and take the derivative. If you do that, it is del f del x, which is nothing but fx, which is exactly equal to 2 minus 2x, which is exactly equal to 0. If you have to equate with 0, again take the partial derivative with respect to y variable del f del y, that means 2 minus y, again equate with 0. So you will end up with a solution, fx is equal to 0, fy is equal to 0, you will give a solution. And what is the solution? X is equal to 1, y is equal to 1, and it is the only critical point, and in that case local maxima exists, because local maxima you have to check. Okay, it is local maxima, local minima. That means the corresponding the point 1 1, you have to talk about the Hessian matrix, and you have to calculate. Okay, since it is a R2 to R, so that means Hessian matrix is a 2 cross 2 matrix. You just have to think about that your determinant should be whether it is positive or negative, along with 1 1 term is positive. So if you do that, then it will say that this is a local maxima. So that is all about the interior point. Okay, so now we next study the behavior of f on the boundary, which is a triangle, Earlier it was a square, now it is a triangle. So on that point I have to see, is there any critical point or some points in there where I have to check, so whether maxima minima exist or not. Okay, so case 1 means what? So that means you have 3 lines, so that means you pick one variable fixed, think about x axis or y axis, and in the line x plus y is equal to 9. So case 1, so I am keeping y is equal to 0, that means I am in the x axis, so that means I am in this line, Again in this line you have y is equal to 0, so that means you put y is equal to 0, think about it as a function of single variable on the interval, and think about is there any critical point exists for a single variable functions. Okay, so that's what exactly I have done. So on the segment y is equal to 0, you just put y is equal to 0, so let phi x is equal to f of x 0, which is, this is the functions defined on the interval, closed interval 0 to 9, because what is the interpretation? So this is actually your 9 comma 0. Okay, so if I do that, then just check the value phi at the point 0 0, which is nothing but f of 0 0, whose value is 2, phi at 9, which is at the boundary point, means at the corner point, phi 9, phi f of 9 0, which is minus 61. So that means at the corner point you have the value like phi 0 phi 9 or f 0 0 f 9 comma 0. And now on the open interval 0 to 9, what will happen? Again you think about as a function of single variable phi x, take the derivative, equate is 0, and get some possible points where might extremum exist. Okay, so if I put phi prime x is equal to 0, it will give you x is equal to 1. So therefore x is equal to 1 is the only critical point of phi x in the interval open 0 to 9. So you check the value. So therefore phi of 1, which is exactly equal to f of 1 0, because y I keeping with y is equal to 0, so f of 1 comma 0, which value is 3. So therefore in the boundary I have, what are the points? In the boundary I have 0 0, 9 0 and 1 0. These are the possible points where extrema might exist, and you have the corresponding value. One is 2, one is minus 61, and another is 3. Case 2, in the segment x is equal to 0, again do the same process, keep x is equal to 0, think about it as a function of single variable y, and just get the things. So put x is equal to 0, think about function of single variable psi y, which is f of 0 comma y, which is these functions. Okay, so you just check the boundary point. Okay, so if I check the boundary point, you will have the value, already boundary point is there. So what will happen? That means okay, so what will be the boundary point? So this should be, that means I am having this one. Okay, so therefore if I put x is equal to 0, then y is equal to 9, again this is 0 comma 9. Okay, fine. So therefore, so you have a 0 0 0 0, already value is 2, it is given f 0 0. Okay, so again we have to find 9 comma 0, f of 9 comma 0, I think have I right? Okay, I have it in. So that means, so this means psi of y. So okay, so let me just fix once again. So you have a segment x is equal to 0, so you have a function psi y, which is f of 0 y, again y on the interval I, which is nothing but 0 to 9. Okay, so now what will be the value of psi 0, which is f of 0 0, which is nothing but 2, I already calculated. And what will be your psi 9, which is f of 0 comma 9, and what is f of 0 comma 9? If you calculate in your function 0 comma 9, so if I go back, so 0 comma 9, so that means x is 0, so that means this is kind of symmetric in x and y, so that means again it will, the value will be minus 61. So on the two corner points I have done. So only in the open interval 0 to 9 you have to see is there any possible critical point. Again I just consider the derivative of psi prime, which is 2 minus 2, so that means y is equal to 1 is the possible, that means x is equal to 0, that means this is the possible critical point. Again the value is 3. Two side I have checked, so only part is remaining case 3, which is nothing but this line. So only this part is remaining, this is the one. Okay. So how to do that? Again here is a relation y is equal to 9 minus x. You just replace y in this function f of x comma 9 minus x. It is a function of single variable, and again you just calculate the critical point in the boundary point like 0, 9 and 9, 0. I already talked about the value of the functions. Okay, this is actually minus 61. So on the open interval you have to consider. So if you consider, you will get, that means you have to just take the derivative of this function. If I write it say g of x. Okay, so that means if I take the derivative g prime, equate with 0, and you will have x is equal to n by 2. Once this x is equal to n by 2, y is also n by 2. So this is possible critical point or possible point where my what is called maxima minima exist. Okay, critical point in that sense actually. Okay, it is in the boundary actually. Okay, so and what is the value? If you calculate it, it is minus 41 by 2. So now I have all the possibilities, right? So in the boundary I have all the corner points in the possible points where it might attain extremum or maxima minima, and similarly in the interior if I have all the values of my functions, then I can combine everything. So therefore f11 it is having the value 4, it is the maximum. So this is the kind of global maximum, and at the point 9, 0 and 0 1 it is taking minus 61. So this is the global minima. This will not work because I am talking about global minima, right? So therefore this 9 by 2 will not work because it is value is minus 41 by 2, which is actually greater than minus 61. And similarly even if I have a point 1, 0, 0 1 which is taking the value 3, however in the point 1 comma 1 it is taking the value 4. So therefore global maximum exists at the point 1 1. Okay, so these are the problem. So once we have a kind of functions, and if you suppose want to find the points of extremum, either maximum or minima, then you have to be always careful. In the interior point you can, of course you have to look for what are the critical points there. At the same time, if your kind of domain is not open, that means it will have a like boundary point, then you have to check in the boundary point as well, and this is one of the boundary points. The boundary is very nice, you just keep one variable fixed and think about it as a function of single variable. The corner point you will check, and in the interval you just again do the single variable calculus and find the possible points where your functions might attain maximum, and then you compare everything, all the possible points your functions attains extremum, and then you say that if at some points which one will be the biggest value, which one will be the smallest value. Okay, so now I come to the concept, or I should say that the constrained extremum. So earlier what will happen, you can see actually. So earlier what will happen, I have a functions f from subset Rn to R, some scalar field, and I want to find the extremum values of f along with extremum points of these functions, but there are no certain conditions. But now if I say that okay, I want the extremum of f subject to some conditions. So that means that point I want to find the points of extremum of the function f, but that point should satisfy something. That means I am putting some extra condition, that means I am putting some constraint. Now those kind of problem, how do I handle it? Whether the earlier method like just get the critical point and see the Bayesian matrix and the corresponding you can talk about the existence of extremum, local or global. So the question is no, the earlier method will not work in this setting. This time if I have a constraint, that means I want to maximize or I want to find the extremum of this function subject to that condition, there is a method called Lagrange multiplier. Using that Lagrange multiplier to make the constrained extremum to the unconstrained extremum like the earlier one, and there you apply the same process. So that's how you can solve it. So that means even if I have a constrained maximum, there is a process called Lagrange multiplier to make it unconstrained maximum, and unconstrained maximum, that means just you have a functions of couple of variables and you have to find whether what are the extreme points, and there it is very nice if your domain is nice. So then you just take the partial derivative, or you can just find the critical points and analyze your Bayesian matrix on those critical points, and depending on the nature you can talk about whether extremum exists or not. Okay, so that's called the Lagrange multiplier. So that's what I've said. So in this lecture we learn the scalar field. Of course f is a function from Rn to R. Now you see I have written it is constraint optimization problem. So that means finding an extremum values of f. Of course I want to find some extremum values of f or some extremum points subject to the equality of constraint gk is equal to, that is the constraint. That means whatever point you will get at which your functions have a global maxima or local maxima, whatever it is, it has to satisfy this constraint. That means gk should satisfy those points. That is called constraints. Okay, and it depends that if I have a finitely many constraints where gk's describe some sets in Rn. Okay, so that means I want to get the extremum values of f subject to some conditions. So that is those kind of problem is called constraint optimization problem, and to handle that problem you have this nice method called Lagrange multiplier method to change, or I think to reduce your constraint maximum problem to the unconstrained one and solve it. Okay, so that's what I have written more clearly. So extremum problem with constraints. What is that? So let f be a real valued functions defined on a domain D subset of Rn. We need to find the extremum values of the functions f on some subset. You see, I am not talking about the extremum values of f on the full set D. Rather, I am talking about some subset S of D, and the subset S can given as the points in D satisfying the equation g of x is equal to 0. So that's the restriction I am putting. So I want to find the extremum values of my functions not on the full domain, on some subset S which satisfies the equation that g of x is equal to 0. So that's what I want to find with some constraint. And what is that constraint? It should be a subset S and which is given or which is satisfying the equation g of x is equal to 0, where g is a function defined on D to R. So that's the constraint I am giving. So that means I want to find the extremum values of f subject to the condition that those points should satisfy the equation g of x is equal. So g of x is equal to 0. That means that constraint I am giving. Now question is how to solve it. Okay. So problem I have written kind of explicitly the extremum problem with constraint. That means find the extremum values of these functions f d subset of Rn to R, where on D subject to the constraint that g of x is equal to 0 for x is in D. That means I want to find the extremum values of f at those point x, and those points should satisfy this equation g of x is equal to 0. So that's called the constraint extremum problem or extremum problem with constraint. So constraint is, this is the constraint actually, how to handle that situation. So let's see some examples before going to the theorem. There is a theorem I will write, that means how the Lagrange multiplier will come, and then using that Lagrange multiplier you can make it constraint problem to the unconstrained one and you solve it. So okay, so example, so where my previous method, that means the earlier one, just you get the critical points and analyze the Hessian matrix. So where is that process will not work in this setting if I have some extremum problem with some constraint. Okay, so first one you see, so minimize your functions f of x y z, which is x square plus y square plus z square, subject to the condition that g of x y z should be 0. So now what we have to do, so that means I want to minimize my functions f at some points. What are the points? Okay, that point should satisfy that g of x y z is equal to 0. So the process is that, so since g of x y z is linear, so that means this is equal to 0. So that means what you do, you just replace or get the variable z, which is 2x plus y minus 5, and you replace in your f, make it a function of two variable. Okay, so earlier you have a function of x y z, right, which is x square plus y square plus z square, but the constraint will give you some restrictions on your variable. So what you do, you get replace one of the variable, that means here I am replacing z in terms of x and y. So now your functions becomes a function of two variable, I am writing as hxy. So that means somehow I want to minimize the function h, so whose first variable x, y, and z is replaced by 2x plus y minus 5. So that means it turns out that your function h is nothing but this one, x square plus y square plus 2x plus y minus 5 whole square. Now to find the critical points you can easily do, as I said, because h is again a function of two variables which is a polynomial. What you have to do, you have to just take the partial derivative, equate 0 and get the solution. So if I do that one, so hx you can easily calculate, hy easily calculate, put hx is equal to 0, that means del h del x, put del h del y is equal to 0, and you will end up with that. This is the solution, 5 by 3 and 5 by 6 as the critical point is at. So now in that case you have to analyze your Hessian matrix. Okay, so in that case the 1 element is a 10 and the determinant is positive. So that means the nature of the Hessian matrix says that at the point 5 by 3 5 by 6 it will have a local minima. Okay, so that means I have said h attains a local minimum value at the critical point, this one. So therefore the point, so now xy is this one. Now subject to the condition that g of xyz should be 0, you have x and y, so that means you can get the point z. So therefore once you have a x and y, you will have z, which is nothing but minus 5 by 6. So therefore this is the point, is a local minimum for f. Okay, so that is one problem. Now look at the second one. Second one is that, okay, I want to minimize this function f of x y z, which is x square plus y square plus z square, subject to the condition that g of x y z, which is x square minus z square minus 1 is equal to 0. That means what are the points x y z? That means I will have the minimum value of f which should satisfy the fact that x square minus z square is exactly equal to 1. Again, repeat the similar things. So you just replace. So I have a g x y z, x square minus z square is equal to 1 is equal to 0. So that means you replace z by in your earlier functions. So you have a z square is equal to x square minus 1. Now define a function h in two variables, which is f of x comma y, and replace z square by x square minus 1, which is nothing but x square plus y square plus x square minus 1 whole square. Now again you have a function of two variable, again it is a polynomial, you just get the critical points. Again if I get the critical points, that means if I make the partial derivative hx equal to 0, hy is equal to 0, then what will happen? I will have the critical point. The method of finding critical points of h yields that 0, 0 is a critical point. However, now once you have a 0, 0 is a critical point, now look, it's a critical point of h perfectly all right, but look, the point is here actually, but there are no points satisfy g of x y z is equal to 0 with x and y coordinates as 0, right? So that means what I have done, so I have replaced z square by xy, right? I am having the function hy, h of xy, and I am trying to find the possible critical points. So what I end up with, that 0, 0 is a critical point of h. That means my x coordinate is 0, y coordinate is 0. So that means now I have to find z, and I have to find z point in such a way that means it should satisfy this one. Now once I have x is equal to 0, y is equal to 0, then what will happen? This will give you actually z square is equal to minus 1, which is not the case. So that means you cannot have a point. So in other words, there are no points which satisfy g of x y is equal to 0 whose both x coordinate and y coordinates are actually 0. So you cannot have any point. So therefore the above method does not work, colleagues, if we apply blindly. So that my point is that since the constraint is that it has to satisfy this one, if I just replace the one of the variable, make it a function of two variable, get the critical points and do that, it will not work. Okay, so that means the earlier method will not work in this setting because of this constraint maxima problem, and that is why I need a different method, and that is why Lagrange multipliers came into the picture. Okay, so that's again I have written once again clearly. So constraint maximum for functions f from Rn to R. So in earlier two examples means I am talking about not the earlier one, actually I am talking about this example, I should say. This is the example. One is that you have to find the absolute maxima minima whose kind of on the set is this one, whose boundary actually line, and similarly you have a boundary is square, the boundary is line. So these two examples I am talking about. So that is written there actually. So in the earlier two examples, the boundary of the domains are lines. So now we discuss a method to deal with more general boundary, because if I go higher dimension, it need not be a line, it could be like a plane, it could be a surface. In that case, how to handle that situations? Since it is in R2, it is perfectly all right. So once I go to more than 2 dimension, then it will be a surface, it will be a plane. There, how to handle those situations. So that's what I have written. So let U subset of Rn be an open sets, f and g two functions from U subset of Rn to R. Suppose these are continuous functions, then what I want to maximize my functions fx, okay, subject to the constant g of x is equal to alpha. So that's the real problem I have to do. Okay, so I have a set U subset of Rn open, f and g are two functions from U subset of Rn to R which are continuous function. I want to maximize, or I want to extremize my functions fx subject to the condition that g of x is equal to alpha. That means what are the points where my functions attains extremum, and that point should satisfy the condition that g of x is equal to alpha. So those kind of problem I would like to handle. So one example I have given, okay, as I said, because since I am having a constraint, so only the interior point or will not work. So that's exactly I have written. So for example, if I want to find the extremum values of these functions on the circles, which is the constraint. So that means I want the extremum values on the points lies on the circle. How to? If you do that, if you just solve with the partial derivative of f with respect to x, partial derivative with respect to y, if I just solve it, okay. So if you do that one, actually what will happen? One of the you can easily check, because it's a very nice function, f of x is equal to x square minus y square, and x square plus y square is equal to 1. So it turns out that f attains minimum at the point 0 plus minus 1 and maximum at the point plus minus 1 0, those points. Although this C gradient vector, they are non-zero. So that means in the critical point what I have. So in the critical point we know that if some points all the first order partial derivative exists, it has to be 0. So therefore the gradient is non-zero, that means first order partial derivative at the point 0 plus minus 1 and plus minus 1 0 is non-zero. So that means it is not a critical point. Nevertheless, it attains a minimum and maximum. So therefore my point is that the earlier one, how I discussed solve the problem of extremum, what to do. So that means that problem, if you apply blindly, it will not work. So here what will happen? It attains maximum minimum 0 plus minus 1 and plus minus 1 0. Nevertheless, these are not the critical point because first order partial derivative exists, but they are not 0 because this is the one. So therefore you should not apply the earlier one blindly, and that is why your Lagrange multiplier came into the picture. Okay, I think this is a test for constraint maximum that I will explain in my next lecture, how to handle those situations. So that means if you want to extremize or if you want to maximize, minimize whatever your function subject to some conditions, then how to handle that situations, and then of course Lagrange multiplier will come, and that I will discuss. For the timing, I think I should stop here. Thank you.